Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 9, Geometric Constructions, Invariants. Section 89, Taylor's Theorem, Polar Forms. It is desirable at this point to borrow an important theorem from elementary algebra. Definition. Given a term, ax sub I to the nth power, of any polynomial, the expression n a x sub I to the n minus 1 power is called the derivative of a x sub I to the nth power with respect to x sub I. In symbols, d over dx sub I, a x sub I to the nth power is equal to n a x sub I to the n minus 1 power. The derivative of a polynomial with respect to x sub I is, by definition, the sum of the derivatives of its respective terms. This definition gives at once d over dx sub I, a equals 0, if a is independent of x sub I. Applied to a term of a binary form, it gives d over dx sub 1, k x sub 1 to the nth power, x sub 2 to the mth power, equals nk x sub 1 to the n minus 1 power, x sub 2 to the mth power, and d over dx sub 2, k x sub 1 to the nth power, x sub 2 to the mth power, equals mk x sub 1 to the nth power, x sub 2 to the m minus 1 power. With this definition, it is possible to derive Taylor's theorem for the expansion of a polynomial. We state it for a binary form as follows. Given the binary form f of x sub 1 comma x sub 2 equals a sub x to the nth power equals a sub 0 x sub 1 to the nth power plus n a sub 1 x sub 1 to the n minus 1 power x sub 2 plus n times the quantity n minus 1 divided by 2 a sub 2 x sub 1 to the n minus 2 power x sub 2 squared plus plus n a sub n minus 1 x sub 1 x sub 2 to the n minus 1 power plus a sub n x sub 2 to the nth power. Footnote: for the proof of this theorem on the basis of the definition just given, chiefly find College Algebra, pages 460 through 462. If herein we substitute for x sub 1, x sub 2, respectively, the expressions x sub 1 plus lambda y sub 1, x sub 2 plus lambda y sub 2, we obtain f of x sub 1 plus lambda y sub 1, x sub 2 plus lambda y sub 2 is equal to f of x sub 1, x sub 2 plus lambda times the quantity y sub 1 d over dx sub 1 plus y sub 2 d over dx sub 2 f of x sub 1, x sub 2 plus lambda squared over 2 factorial times the quantity y sub 1 d over dx sub 1 plus y sub 2 d over dx sub 2 close paren squared f of x sub 1 comma x sub 2 plus plus lambda to the nth power over n factorial times the quantity y sub 1 d over dx sub 1 plus y sub 2 d over dx sub 2 close paren to the nth power f of x sub 1 comma x sub 2. Here the parentheses are differential operators. Thus, the quantity y sub 1 d over dx sub 1 plus y sub 2 d over dx sub 2 close paren squared f equals y sub 1 squared d squared f over dx sub 1 squared plus 2 y sub 1 y sub 2 d squared f over dx sub 2 dx sub 1 plus y2 squared d squared f over dx sub 2 squared, where d squared f over dx sub 1 squared means d over dx sub 1 of df over dx sub 1. d squared f over dx sub 2 dx sub 1 means d over dx sub 2 of df over dx sub 1, etc. It is readily proved for any term of a polynomial, and hence for the polynomial itself, that the value of such a higher derivative as d squared f over dx sub 2 dx sub 1 is independent of the order of differentiation, i.e. that we have d squared f over dx sub 2 dx sub 1 is equal to d squared f over dx sub 1 dx sub 2. Definition: the coefficient of lambda in the above expansion, namely y sub 1 df over dx sub 1 plus y sub 2 df over dx sub 2, is called the first polar form of y sub 1 comma y sub 2 with respect to f of x sub 1 comma x sub 2. The coefficient of lambda squared is called the second. The coefficient of lambda to the nth power is called the nth polar form of y sub 1 comma y sub 2 with respect to the form f. If any polar form be equated to 0, it represents a set of points which is called the first, second, nth polar of the point y sub 1 comma y sub 2 with respect to the set of points represented by f of x sub 1 comma x sub 2 equals 0. Consider now a binary form f of x sub 1 comma x sub 2 equals 0 and the effect upon it of a projective transformation pi. X sub 1 prime is equal to alpha x sub 1 plus beta x sub 2. X sub 2 prime is equal to gamma x sub 1 plus delta x sub 2, where alpha delta minus beta gamma is not equal to 0. If we substitute these values in f of x sub 1 comma x sub 2, we obtain a new form, f of x sub 1 prime, x sub 2 prime. A point x sub 1, x sub 2, represented by f of x sub 1, x sub 2 equals 0, will be transformed into a point x1 prime, x2 prime, represented by the form f of x1 prime, x2 prime equals 0. Moreover, if the point y sub 1, y sub 2 be subjected to the same projectivity, it is evident from the nature of the expansion given above that the polars of y sub 1, y sub 2 with respect to f of x sub 1, x sub 2 equals 0 are transformed into the polars of y sub 1 prime comma y sub 2 prime with respect to f of x sub 1 prime, x sub 2 prime equals 0. We may summarize the results thus obtained as follows. Theorem 6. If a binary form f is transformed by a projective transformation into the form f, the set of points represented by f equals 0 is transformed into the set represented by f equals 0. Any polar of a point y sub 1, y sub 2 with respect to f equals 0 is transformed into the corresponding polar of the point y sub 1 prime, y sub 2 prime with respect to f equals 0. The following is a simple illustration of the polar of a point with respect to a set of points on a line. The form x sub 1, x sub 2 equals 0 represents the 2 points whose non-homogeneous coordinates are 0 and infinity, respectively. The first polar of any point y sub 1 comma y sub 2 with respect to this form is clearly y sub 1 x sub 2 plus y sub 2 x sub 1 equals 0, and represents the point negative y sub 1 comma y sub 2. In other words, the first polar of a point P with respect to the pair of points represented by the given form is the harmonic conjugate of this point with respect to the pair. Exercise: determine the geometrical construction of the n-1th polar of a point with respect to a set of n distinct points on a line. Chiefly Exercise 3, page 51.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.